back and look. Okay, so here's the deal. Vector valued functions are different than functions we studied in the past. In this way, functions we studied in the past, they've been real numbers to real numbers. So you input a real number, you get out a real number. And that's not going to be the way it is with vector valued functions. The vector valued functions, we're going to input a real number, and we're going to get out a vector. And the vector valued functions, I look upon them as like a package of functions. Generally speaking, we'll denote it with an R, and the variable will be a T. Now, in dealing with vector valued functions, it's going to be just like when we dealt with parametricized curves. So what we have here is we have a function, R of t, and it's going to give a vector. The x-coordinate is going to be some function of t, and the y-coordinate will be some function of t. Now this is a vector valued function on the 2 dimensions. And notice that, we could write it this way as well. Don't forget, we could write it as f of t I plus g of t j. That's another way that we could write it, of course. It's just whichever way you want, whichever way you feel most comfortable with as you're working with these. But notice it's a package of functions. And when we input a value of t, we get out a vector. Now, I want to illustrate this by thinking about this function. Let's think about a curve on the 2 dimensions, and we will say, okay, this is the curve. Y equals 4 minus x squared. Now, we know how to graph that, of course. We can plug in x values, we get out y values, and we soon get a curve. Now, when we're dealing with a function like this, we really don't pay much attention to which way the thing is being sketched. In other words, which way the curve is being formed. All we care about is that this is a parabola. It has a maximum that occurs at 0, and that maximum is 4. And we know what it looks like. It's an upside-down parabola. Well, what we do when we talk about vector-valued functions, and we want to represent this curve, we would end up parametricizing it. So what we would do is we would say, we would do just like we've done before when we work with parametric equations. We might say, well, I'm going to let x be t. This is a simple one. And then y will be 4 minus t squared. Like that. And now we have a vector-valued function. And I might say this. And this is important. I need to give some indications about the boundaries for t. I'm going to say t starts at -2, and it goes to +2. So I've got this vector-valued function, and remember, this is like it's like a package of these functions. You've got a function here of t, and a function here's a function of t, here's a function of t, and they're going to give us a vector. Now, here's the way these work. If I want to find r of -2, all I do is I put a -2 in for t. And so this would be 4 minus -2 squared. Of course, that is -2, 0. And this gives me a vector. Now the question is, well, what do I do with that? In other words, how can I represent that graphically? Well, this represents a vector in standard position. In other words, we think of this, and we're going to plot these as a vector that has its initial point, the origin, and this is the terminal point. So we look upon this as a vector that has a terminal point at -2, 0, and has initial point at the origin. So for example, I could, if I wanted to represent that function, I would do it that way. Okay? So it starts at the origin and goes to that terminal point, -2, 0. That's the way you would represent it. Now, if I do this, I could say, well, let's try r of -1. Well, that would be -1. And then, of course, I have 4 minus -1 squared. And that would give me -1, 3, right? -1, 3. So that particular vector would go like this. We have -1 and up 3, right? So there it goes, like that. Now, what happens here is we look upon the terminal points here as forming a curve. So when we plot these vectors, we're looking at the endpoints of which form a curve. So now you can see right away, you can say, well, what about r of 0? And r of 0 would be 0 and 4. Whoops, r 0 and 4, okay? So if we were plotting that vector, it would go this way. Start here and go up to 4. And there it is. And we could keep going around like this. And what you would see is we know what a parabola looks like. It would end up, we would have a curve. That's kind of an outline of it. We only plotted a few points. But if you go back and you could say, well, I can go at the terminal points here and kind of sketch the curve. Okay. This is a curve that was generated by looking at the terminal points of those vectors. And when we do this, it's important to indicate a direction. So when you're graphing a curve from a vector valued function, you of course want to indicate the direction. Because we could have this go the opposite direction. The same curve, we could represent it with different x's and y's, and we could get a curve going in the opposite direction. So we want to always indicate the direction. And that's going to be important later on when we're talking about position and we're talking about velocity and that sort of thing. Because it matters which, the direction when we're talking about velocity. Now, there's some parameterizations that we really need to be aware of, or we need to think about. For example, x squared plus y squared equals let's say 4, right? Now, we know that that's a circle of radius 2, right? So this is a circle of radius 2. And if we want to come up with a parameterization for that, we could say this. Well, x is going to equal 2 cosine theta, or t. We could just use t. Let's stick with t. And y is equal to 2 sine t. Now, we don't have to do it that way. X equals 2 cosine t, y equals 2 sine t. That will give us what we want. And in fact, we could write a vector valued function this way. We could say this is equal to 2 cosine t, 2 sine t. And that would be our circle. And then we could say, well, t goes from 0 to 2 pi. Okay? And that's going to give us a circle that it will give us the same curve as this circle here. Okay? And that will generate a circle, that will generate a curve that goes in the counterclockwise direction. Right? Okay? So if I were to sketch this circle, of course it would look like that, and the arrows would go this way. Okay? Now, we could represent this same curve a little differently. We could represent it this way. We could say, well, let's try this. Let's do 2 sine t for x, and y equals 2 cosine t. And this would be fine and dandy. We could do that. Our vector valued function would look a little different. I mean, it would look, just slightly different. We would have 2 sine t, 2 cosine t, and we could say, well, t is still going to go from 0 to 2 pi. The difference it would be exactly the same curve if you look at it. However, the curve would be sketched in the opposite direction. So you'd still get a circle with radius 2, but it would be sketched in the clockwise direction. So we're not used to seeing that. We're used to seeing cosine for x and sine for y. It doesn't have to be that way. If you're parametricizing a circle, you can have it go whichever way you want. Okay, so this is a vector this is a vector valued function in just 2 dimensions, right? We have the x and the y. Now, one more I want to look at before we go on in the x and the y is a line like this. A big part of what we're going to do in the near future is take a curve and parametricize it. Now, there are some key ones that you need to be able to work with. And one is a circle. We immediately need to be able to parametricize a circle, and later a sphere. But a circle is very important. Another one is a line. We need to be able to really quickly parametricize a line. Now here's a line, and notice it has this point. It goes 1, 2, 3, 4, 5. This point, this is 5 on the x-axis, and then up here 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9 on the y-axis. What I need is a curve, a vector-valued function that will generate that curve. And if that's all the instructions I'm given, I don't even care which direction it goes. I don't care if it goes from left to right or right to left as it's being sketched. But here's what I can do. I know this, that I can just set this out. I can say, well, when t is 0, I want the y to be 9. I could do that. In other words, I want the y-coordinate to be 9. And I could do this. I could say, well, when t is 1, I want the y to be 0. See, I just set the parameters as I see fit. 0 and 1 are pretty simple. So let's see what I can do. Now, if I do this, let's see what would be a good one. So let me just deal with the y's here. When t is 0, I want it to be 9. So what if I did this? What if I did 9 there, and I said this, minus t? Now that won't work, will it? Because when t is 1, I have 8. Okay? What if I do this? What if I say when t is 9? Well, that'll work too, right? I mean, look, now, when t is 0, I get 9. When t is 9, I get 0. Ah, okay, I might be onto something there. That 0 and 1 sounded nice, but I'll just make it 0 and 9. Now, what about x? So when t is 0, I want x to be 0. And when t is 9, I want x to be what? 5? Is that something we can make work? What could I put in here? Anything? Look, okay, what if I do this? What if I do 5/9 t? Would that work? Ah, that will work. Right? And that's all I need. I just need a line that meets the qualifications, right? Because look, when t is 0, I get 0, 9. When t is 9, I get 5, 0. So that works, right? Now, you could have engineered a different one, and you could have said, well, I want t to be 0 and 1, and you could have engineered something else. If I wanted t to be 0 and 1, let's look at an alternate. Well, if I want it to be 0 and 1, I could do this. I could do 5t here, right? Because when t is 0, I get 0. When t is 1, I get 5. Sweet. That works. Well, what would I do over here? 9 minus 9t, right? Would that work? Yeah, I think that would work. Okay, so that's good. And then this one is when t goes from 0 to 1. So you can see there's an infinite number of ways you can parametricize this line. And later on, we're going to work more with that. But anyway, you can play around with it. And maybe if you're working on a problem, you'll get something different than the back of the book, but that's okay. Now, whoops, I meant to do, let's see. Okay, So we've done two-dimensional vector valued functions. Now a three-dimensional vector valued function is going to be notated the same way. I'm going to use, generally I'll use R. But this time I'm going to have a component for the x, and it's just a scalar function where you put in a real number, get out a real number, a y, and now a z. Okay? And of course you can write that this way, f of t I plus g of t j plus h of t k. You can write the vector valued function either way. So with vector valued functions, we still, everything works the same way, except when you're dealing with a vector valued function with two parts, the x and the y, you've got a curve on the xy axis. When you're dealing in 3 space, now you've got what they call a space curve. The other was a plane curve. This is a space curve. So it's just a little more complex. So you might have things like this. You might have a curve that's defined this way, where you have maybe 2 cosine t, 2 sine t. Okay. Now, so far so good. We know that's a circle. But then let's suppose that we do a comma over here and we have maybe a 5. Okay? Now, so we added an extra dimension. So now this is a space curve. And if you think about it, this part of it gives you a circle. This part of it raises it up 5 units. So what you have is you have a circle, okay? A circle being formed, and then the vector points up at 5 for z coordinate, right? So this is a circle that's hovering up here above the xy plane at 5, right? That's what that is. So that's very easy, and we need to be able to recognize that. Now, you can add a little pepper to it, spice it up a little bit, and you can say, well, let's change it and say, okay, here's 2 cosine t, 2 sine t, and comma t. Now as t changes, z changes. Now it still has this spiraling characteristic, right? Because we've got the thing that still acts like a circle. However, the t keeps being increased. So let's see if we can, let's see if we can figure out what that might look like. First of all, down here, I'll just go over 2 units and maybe make a base here and then go up. Notice I've just gone over 2 units on the x and y, maybe. So you've got a little cylinder there. And what's happening with this, and I'm not very good at sketching these, but what's happening is, you have something coming over here, and it goes behind, right? Okay, something like that, and it's being sketched this way. See that? So it's a cylinder type thing, right? It's a spiral. Spirals up. And remember, what we're looking at is we're looking at the terminal points of all these little vectors that are pointing away from the origin. Now, what I've done here is I've went ahead and sketched this thing on Maple because I want you to see how you can use your Maple to get these curves. A lot of times you'll try sketching something with Maple and it won't work. And what you have to do is you have to, first of all, enter this command with parentheses plots. And I guess it just summons up the plotting package. Because after you do that, then, I don't know if you can see this very well, but like we want to plot this vector, the values of this vector function. So the command is space curve, parentheses, and then you put a little bracket. I had cosine t, sine t, and t. Now notice I didn't put the 2 in there. This is just, it wouldn't be much different with the 2, right? This has a radius of 1. And then I closed it. I closed the brackets, and I said t equals 0, dot, dot, 4, and you have to do times pi, times pi. And when you do that, you get, of course, a spiral. And you can see I took the screenshot of it to show you kind of how it spirals up. Does everybody see that? Okay. Yep. Yeah, it would look like circles. Yeah. Because it is making circular patterns, and because you're standing off over here to the side, you can detect that. Okay, any questions? Any other questions? Okay, now one other thing I want to look at is we're not going to get heavy into this right now because later on we're going to look at differentiation with vector valued functions. But when we talk about limits with vector valued functions, you evaluate limits about the way you think you would, because think about it. If you've got a vector valued function and you've got f of t, g of t, and h of t, okay? So you've got this vector valued function, and you want to talk about the limit. And remember, we're just introducing it here. Let's suppose I have this limit that t goes to a, something like that, of this vector valued function. Well, if you think about it, the vector valued function is giving you a package of 3 functions. It's like saying, here, find the limit of each one of these functions. I mean, these are just scalar functions. They put out a real number. They're functions like we're accustomed to. So if we're talking about evaluating this limit, it involves just evaluating the limit of each and every one of these. And then all we know about limits applies. Okay? So when we talk about limits, everything you know about limits applies for these. So let's look at a vector valued function here. Let's suppose we have t goes to 3, and, well, let me write the function first. Let's suppose we've got this nice vector valued function here, e to the t, and we'll do t squared plus 3 and 4t. Just some random vector valued function. And we talk about the limit as t goes to 3. Well, you know how to evaluate a function. The limit of e to the t as t goes to 3 be the same way, e to the 3. Here you have 3 squared plus 3. That's 9. That's 12, right? And then 4 times 3 is 12. So there is the limit. And everything you know about limits still applies. The factoring, the canceling, you just think of these vector valued functions as a package of functions. And if you're asked to take the limit, it means, okay, I've got to take a limit of this package of functions. Okay? Y'all see that? Now, also, if you want to talk about continuity, if you're wondering, well, I wonder if this space curve is continuous. Well, here's the thing. A space curve is continuous at a point if this is true. If the limit as t goes to a of r of t is equal to exactly the same thing as r of a. In other words, if those two things happen, it's just like with scalar functions when we were first introduced to continuity. If the limit is the same as just plugging into the function, then we say that the function is continuous at that value. So if this happens, then r of t is continuous at t equals a. Okay? If that happens.